beta, and that shows that it's a beta decay. I personally don't like that so much because it's easier to get confused. So, because what else this is also going to show, in the way that I'm going to do it, is the loss of that electron, because we don't want to forget about that. So I'm going to write it with an E. So we see that we have carbon, and we're going to kick off that electron, and when that happens, the neutron is going to change into a proton. So we're not, now, so if we think about it, we're not getting rid of any neutrons or protons, so we're just changing one into the other, but the number's still going to stay the same. So when we move over to this last element that we're creating, in a sense, is we still have number 14. That will stay the same. Now, what we did do is we took that neutron, which was unaccounted for on this bottom row, and we changed it into a proton, which is accounted for on this bottom row. So that will turn into 7. Now, what do we know when we have a change in the atomic number? We change the element. So we no longer have carbon, but we have nitrogen 14. And that is a beta decay. It's the change of a neutron to a proton, kick off an electron. It's pretty simple. So let's do one more example real quick. Okay, so we have thorium-234, which is a pretty common radioactive element. It's not something we really see a lot in just general chemistry or organic chemistry, but this is something that we will see when we get more radioactive because it's such a heavy element. So we have thorium-234. We're going to kick off the electron, and that will also change one neutron into a proton. So we don't really affect the mass number, but we do affect the atomic number. And so what we'll see is the atomic number, or the mass numbers stay the same, but the atomic number will change from 90 to 91. So we have 91, a -1, which will equal 90, and that's how that adds up. And that's why we represent that as a -1 for the atomic number during the beta decay. Now we'll turn it into practiconium 234. So that's beta decay. Now lastly, what we're a little more familiar with is gamma decay or gamma radiation. So this little funky looking Y is a gamma. It's a lowercase Greek symbol for gamma. That's how that is written. So when we write this, for example, we're going to use plutonium, which I believe most everybody has heard of. 2, 1, 4, 94. Okay, so we're going to start off with plutonium-240. Now, plutonium is very radioactive in itself, and it's not going to stay in that state for very long. Now, another thing about plutonium is it has a lot of built-up energy. So, when that is the case, we are going to write it not just like this, but we're going to add something to it. We're going to add a little asterisk. This asterisk is saying that this molecule, or this element in itself, has a lot of built-up energy that's really excited in a way. So, what we're going to write is we're going to write its gamma radiation. So we write the gamma particle. Now, we're not losing anything. We're not losing any atoms. We're not losing any atoms, We're not losing any protons. We're not losing any neutrons or even electrons. So no mass is being emitted, so we're going to keep that at 0. And we're not losing any protons, so we're also going to keep this at 0. So if we're not losing any protons or neutrons, then this all stays the same. So we're going to add plutonium 24094. So the only thing that we did different was we took away this little asterisk. So we just took a lot of energy away. That is a gamma radiation. Now, well, this won't just naturally happen sometimes. Sometimes it will, but sometimes, and most of the time, it actually happens in accompaniment to the alpha or beta decay. So during alpha decays or beta decays, a lot of energy is released. So that's my example for gamma radiation. Now, why does this matter? Now, like I kind of joked about earlier, nobody's going to turn into the Incredible Hulk with any amount of gamma radiation, but there are certain types of radiation that can be harmful to humans and especially our health. So let's go back to the three. What did we have? We had alpha decay, beta decay, and gamma decay. So when alpha decay happens, a little bit of radiation is emitted that will be absorbed by humans. Now, the amount that's needed to be damaged is not going to be produced by an alpha particle. Stuff like a piece of paper, substances as thin as paper or skin can block the harmful radiation from getting to our bodies. So alpha particles and alpha decays really aren't something that we have to worry about. So let's go to beta decay. Now, beta decay is a little more powerful, but again, it doesn't take much to block it. Foil. All you really need there is aluminum foil. A thin sheet of metal kind of will block any beta radiation from being harmful to the human body. So, again, not also something that humans need to really worry about much, but what we do need to worry about is gamma radiation, and this is why I think it's so popularized in movies and just mainstream media and what have you, is because it is dangerous. Now, nobody's going to turn into a monster, but there is cell hemorrhage shock that can happen. There can be a lot of cell damage that can happen. You can get burns from certain types of gamma radiation, and that's something that even heavy metals like lead or gold can't fight against or can't resist all the way. So gamma radiation is going to be very dangerous and something that humans need to avoid. Now, thankfully, most gamma radiation is going to happen in a lab, and it also happens in small enough doses that we won't really see it in everyday life. But that is what have you. So those are the three types of nuclear chemistry that we're going to talk about today. Of course, there are more, but these are the basic stepping stones of nuclear chemistry. Thank you.